will be on the convergence to equilibrium for some parabolic-hyperbolic time-dependent Ginzburg-Landau-Maxwell equations. The outline of my talk is as follows. First, I will give an introduction of the Ginzburg-Landau-Maxwell system and record some related results. And then I will present my main results and then give some features of the problem and give a schedule of the proof. And this is a joint work with Professor Glacelli from Milan, Italy, and my supervisor Hao Wu from Fudan University. Now we consider a superconducting material in a bounded domain, a two-dimensional bounded domain with a smooth boundary condition. And the material is supposed to near a critical temperature. So our model is isothermal. And it is well known that the behavior of this kind of superconducting material can be described within Ginzburg-Landau phase transition theory. And for more references, we can refer to a book by Hoffman and Tang in 2001, and also a book by Fabric and Morrow in 2003. And for the material, the state variables are the following. The first one is the complex order parameter, whose squared modulus represents the concentration of the superconducting electrons. And the second one is the electronic magnetic vector potential, and its curl is the magnetic field. The third one is the electric potential. The system we are considering is as follows, which has been analyzed by Tsutsumi and KAIST in 1999 and Battery and Gatti in 2006. The first equation is for the complex order parameter psi, and the second one is from the Maxwell equation. And the right-hand side of the second equation is the total current of the system. And the first one, the blue one, is the displacement current. And the second one is the normal current. The third one is the supercurrent of the superconducting material. And the third one is a transport current due to an external magnetic field. And here we just simply denote some operators by dA psi and dA square psi. And the system is subject to some boundary conditions. We have three boundary conditions, and the second one is non-homogeneous boundary condition. And we say this system is a parabolic-hyperbolic type because the first one looks like a parabolic one, and the second equation, because of the blue part, it looks like a hyperbolic equation for capital A, but it is coupled with the electronic field. Here are some notations. Simply, the curl is we consider in the two-dimensional, so the curl is simply like this. And for the sake of simplicity, we assume the external magnetic field is time independent. And in the two-dimensional case, it is the scalar function. And here, some physical parameters of the system. Lambda is simply the Ginzburg-Landau parameter. And the epsilon is the dielectric coefficient. And sigma is the electronic conductivity parameter. And capital N is the unit out normal to the boundary, gamma. Now we come back to our system. The difference of our current system from the classical one is the blue part. Usually, people consider the Ginzburg-Landau system for the first equation and the second equation without the blue part. It's called a quasi-steady approximation. And in that case, the blue part, namely the displacement current, is neglected. And this well-known system was proposed by Grove and Elizabeth. There's huge literature on this subject, and I will skip it. And there's some motivation to consider this kind of hyperbolic-parabolic coupling system. For instance, in the modeling paper in 2005, the author suggests that if we want to take into account the surface charge of the material, and the author suggests that we keep the displacement in the system. And as I have mentioned, we consider the system in two-dimensional form, and the current system is essentially two-dimensional. Of course, all the results I will present are true for the three-dimensional case, but it's just a mathematical extension. Actually, there are some papers saying that physically in 3D, Ginzburg-Landau equation in a bounded domain, in the boundary, we have this kind of system, and outside of the boundary, we have to couple with Maxwell equation, and we have added some additional interface boundary condition on the boundary. So essentially, our model is only the two-dimensional. A very important property of Ginzburg-Landau equation is the gauge invariance. We can check that for any real scalar valued function chi, which can depend on x and t, our system is invariant under this gauge transformation. And the gauge invariance, mathematically speaking, it reflects the lack of uniqueness of the solutions of the equation. And the invariance of the gauge only defines equivalent class of solutions. And after we impose gauge, then we can prove the uniqueness of the solution. And physically speaking, the transformation under the gauge does not change the macro states of the superconductor. For instance, the macro states of the superconductor are presented by the electronic field, the magnetic field, the density of the superelectron, and the density of the supercurrent. All these quantities are invariant under the gauge transformation. So this means that if we choose a particular gauge, this does not affect the physical state of the material. So we can fix the gauge to fix the unique solution of our system. There are several important gauges in the literature. The first one is called the Coulomb gauge, or the London gauge. And this, we will take this one in our paper. And in this case, we have to look for the gauge chi, and the existence of the gauge chi has been proved in the former papers, for instance, by Liang Jing and Tang Qi in 1995. And another important gauge is the Lorentz gauge. And this also has been analyzed in many previous papers. And also we have the zero electric potential gauge, which they simply set the electronic field to be zero. And this has been analyzed by Du Chang and Lin Huang in 1997. For the original system, we noticed that we have non-homogeneous boundary condition, and it is sometimes more convenient to study this system with homogeneous boundary condition. So we can do the following transformation. We solve this kind of boundary value problem, and actually we can say that there exists a unique solution to this kind of boundary value problem, which is the unique minimizer of this functional in the domain D. And it has been proved in this paper that the mapping of the external magnetic field to the electronic magnetic potential, vector potential, is continuous from H alpha to H alpha plus 1. Here the bold letter, which means the vector space. And in our case, we just assume the external magnetic field belongs to H1, and then the corresponding solution A external belongs to H2. And then we make this transformation. We know that A tilde is the original variable, and A is the transformed one. So finally, we come to the following system. The first one is for the complex order parameter, and the second one is for the electronic magnetic vector potential, and the third one is somehow like the Lagrange multiplier of the Coulomb gauge. You just take the divergence of the second equation and you arrive at the third equation for the electronic potential. And now we are dealing with the homogeneous boundary condition for the new variables, and this system is also subject to some initial conditions. Here is some functional spaces for our system. We denote capital X to be the space for the electronic magnetic vector potential A. And the X0 is the completion of X in H10. And this space is for the electronic potential. And finally, we work with the phase space. The first one is for the complex order parameter psi. And the second one is for A. And the third one is for the time derivative of A. And the fourth one is for the electronic potential psi. And this phase space is a closed subset of the following finite space. And we notice that in the phase space we work with has a constraint. And this is due to for our system we have certain kind of maximum principle. Some known results. In 1999, Tutumi and KAIST used the Galeckin approximation method to prove the existence and the uniqueness of the problem, both in 2D and 3D. And in particular, they show that if the initial data, if the modulus of the initial data for the order parameter is less or equal than 1, then it holds for all time. So that's why we can work in the phase space with this kind of constraint. And then later on, in the paper by Berti and Gatti in 2006, they focus on 2D case, which is, has a more physical meaning. And they show that for any initial data in the space X0, the problem generates a strongly continuous semigroup on the space. And in particular, if the initial data belongs to this phase space, and so that's the solution. And moreover, they show a uniform bound of the solution in the X0 norm for all time. The C only depends on the initial data of the system and also the physical parameter. And in their paper, they also proved the existence of global attractor and exponential attractor. And basically, this is somehow the asymptotic behavior of the trajectories of the system starting from any bounded subset of the phase space. So, the existence of the global attractor means describes the long-time behavior of a family of trajectories. Usually the structure of the global attractor is quite complicated. The goal of our paper is as follows. We look at the asymptotic behavior of a single trajectory. Namely, we want to analyze the following thing. For any initial data in the phase space, and we know that we do not require the initial data is close to a certain equilibrium. It's arbitrary. And we want to ask the question whether the global solution converges to a certain single equilibrium as time goes to infinity. The equilibrium of the system satisfies the following stationary problem, namely the time-independent Ginzburg-Landau equation. And due to this kind of nonlinearity, we know that the function of the time-independent Ginzburg-Landau equation is non-convex. So basically, we do not have the uniqueness of the equilibrium state. And there's a huge literature on this kind of time-independent problem, and I will not say too much about this. Our main result is as following. We prove that for any initial data belongs to the phase space and the global solution of our system, convergence in the phase space to a unique equilibrium, and the psi infinity and the A infinity is the solution of the stationary equation. Moreover, we can provide a convergence rate in the phase space norm, and the convergence rate depends only on this exponent theta, and the theta is a positive constant between 0 and 1/2, and it depends only on the steady state. The proof is based on the so-called Lorentzovich-Simon approach, and this approach was first applied to the PDE problem by Simon in 1983, and then Simon's proof is greatly simplified by Gendobi in 1998. And this kind of approach has shown its power in the study of long-time behavior of several kinds of evolution equations. For instance, the parabolic equation, the wave equation with damping, and the Ginzburg-Landau equation. I mean, here the parabolic type, and also the Convergence equation, and the non-isothermal phase field system, and also some. We can get some results on the liquid crystal flows. We remarked that some similar results hold true for the parabolic type of time-dependent Ginzburg-Landau equations. For instance, in 1997, Liu Chang and Lin Banhua proved the convergence to equilibrium for the Ginzburg-Landau equation with zero potential gauge. And in the paper by Farelso and Tak in 2001, they proved the case for the Lorentz gauge. But by so far, there's no result on the parabolic system. And I have mentioned that for the sake of simplicity, we just assume that the external magnetic field is assumed to be time independent. However, our results hold for the time-dependent external magnetic field. Provided that this kind of external magnetic field is asymptotic stable, namely, itself can converge to a certain function as time goes to infinity. Of course, in this case, the convergence rate of the solution to the limit function not only depends on the Lorentzovich component theta, but also depends on the convergence rate of the external force. Some features of our problems are as follows. Because we are dealing with a hyperbolic equation for the electronic magnetic vector potential, it's not like the parabolic equation that the solution has the smoothing effect. So we have to show the pre-compactness of the trajectory. And this is done by a certain proper kind of decomposition of the solution, and done by Bertrand and Gatti in 2006. And in order to use the Lorentzovich-Simon approach, we have to introduce a suitable Lorentzovich-Simon type inequality. I will show this later. And finally, in order to use this kind of approach, due to the hyperbolic nature of the system, we notice that the dissipation in the basic energy law cannot control the term in the Lorentzovich-Simon inequality. So we have to, for the hyperbolic problem, we always have to produce more dissipation from the system to apply this approach. We'll see this later. So for instance, for the pre-compactness of the system, we just make a decomposition like this. We split the solution into two parts, And we can show that the first part is stable. It converges to 0 in the norm of x naught to exponentially. And the compact part, it is uniformly bounded in a high order norm, x1. So we can get this kind of asymptotic compactness of the trajectory. And the second, we define the functional E naught, and it is important to say that our system has a Lyapunov functional, which is E naught plus the remaining 2 times. And the Lyapunov functional is decreasing with respect to time. We can see that all these terms on the right-hand side is negative. And here we know that this psi is a complex order parameter. We just write it in the real form. And the existence of a Lyapunov functional is the key point of our proof. So based on the precompactness and the existence of the Lyapunov functional, we can say that our system is a gradient system. And from the well-known result by Jack Hare on the dynamic system, we can see that for any initial data in the phase function, its omega limited set is not empty and a compact and a connected subset in the phase space. And the omega limited set consists of equilibrium where psi infinity and A infinity solves the stationary problem. That means the omega lambda set is a subset of the solutions of the stationary problem. Why here we have to use the Loesch-Simon approach? First, from this kind of result, we only know the sequence convergence of the solution. For instance, you give sequence Ti tends to infinity, you can extract a subsequence which can convergence to certain points. But if you have another sequence, the limit function may be different. So we do not know how many points are in the omega lambda set. And on the other hand, I have mentioned that the solution set of the stationary problem is complicated. Although we know that the omega lambda set is a subset of it, however, we do not know the structure of the omega lambda set. In some cases, we can show that the set of equilibrium contains equilibrium continuum. So maybe the omega lambda set can contain some continuum. And due to the fact that omega lambda set is connected, so in this case, the asymptotic will be very complicated. However, by the Loesch-Simon approach, we can show that the omega lambda set contains only one point. So its structure is very simple. It contains only one point. The convergence of the time derivative of A and the electronic potential is very simple. It can be done by the energy estimate. It's easy. So I do not dwell on this. And we'll have a look at the Loesch-Simon type inequality used in our proof. We write the functional E naught in the real form. And the lemma tells us that for any critical point of E naught, there exists constant beta larger than 0 and theta between 0 and 1/2. These two constants depend only on the critical point itself. And for any function belongs to the space X, and if this point is sufficiently close to the critical point, then we have the following inequality. It compares the difference of the functional to the power minus theta. by its Fresher derivative. And then we have a similar result for the Lorentz gauge in 2001, and we can modify their proof to get this kind of inequality. Now we go to the third point, why we have to, why hyperbolic problem is not easy. We just look at the Lyapunov functional, and then the dissipation of the system looks like this. And we find that, unfortunately, these four terms cannot control the derivative, Fresher derivative of E naught. This is the key point of our proof. And we know that in the parabolic equation, it's just the same. The dissipation is the same as the right-hand side of the Loyer-Savage-Simon inequality. And a usual way to do this is to introduce some modified functional, which is the original Lyapunov functional plus some perturbations. However, it's not easy to find those kind of perturbations. It highly relies on the structure of the equation. So this is our new functional. Capital E is the original Lyapunov functional, and we have another two additional terms. And here theta and theta 1 should be determined very carefully with the, it's chosen sufficiently small, and it itself has some relations between them. And the first perturbation looks like this, and the second one looks like this. I just find this and do not know whether there's a general way to produce such kind of perturbations. So for the new functional, we have another dissipation relation. So the time derivative of the new functional is also negative. And we can see that now on the right-hand side of the inequality, we have more terms. And in particular, the blue terms can now control the right-hand side of the Loyer-Savage-Simon inequality. So we have get enough dissipation of the system. Finally, I just show an idea of the proof. From the dissipation of our functional, we can see the L2 norm of A, the derivative, time derivative of A to the square, and the L2 norm of psi 1 t and the L2 norm of psi 2 t from the integration from a certain time t naught to infinity is finite. However, this dissipation relation cannot give us any information on the convergence of A and the psi. So the key point of the Loyer-Savage-Simon approach is like this. Since the omega lambda set is non-empty, so we just pick one, and we have a time sequence such that the solution converges to this one. And we estimate the time derivative of F minus the stationary energy to the power of theta. And then we insert the Loyer-Savage-Simon inequality into this time derivative. Finally, we find that we can deduce the following relation. Comparing with the above one, we find that the power 2 here is reduced to power 1. And this indeed gives us, for instance, the convergence of A in the L2 norm, the convergence of psi in L2 norm. So in this case, in this way, we get the convergence of psi. And also by the compactness of the solution, we can get the convergence in high order norm. Finally, we just say something about the convergence rate. The convergence rate of the solution comes from the decay of F minus the stationary energy. And we can the decay rate of this directly implies this kind of decay rate of solution. And by constructing some proper differential equations, we can use the bootstrap argument to raise the same, to keep the same convergence rate for high order norm in the free space. So that's basically my result. Thank you very much.